room talks to me. And then that gets us going faster, right? Because if I teach at the level of the person who talks to me, right? So that the danger is that everybody else gets lost, right? So what we really need is that the people who are struggling talk to me, right? And if you want to know how best to learn any material, it's to teach other people. So the best way to learn the material is to find the person in the room who's struggling the most and teach the material to them, right? It's really to your best interest, right? Because that's when you know, do you know it, right? Everybody kind of good? Feel free to, as we've done already, feel free to ask questions. So if you search for Jeff Edmonds' homepage, you get this, and then our course is 1090, but this button here is my quick way of getting it to here. README just says, you know, I give you slides and I give you videos, but it really does help to come to class and talk to me. It also says that there's literally thousands of slides, so don't print them, all right? That it just kills too many trees. Not to mention they're interactive. Things come and go, so they don't print that well. Marking says that we're going to have 2 tests and an exam. I find if we have take-home things, then everybody copies off of each other anyway, and then I try to make them hard, and then they're too hard, and then people get discouraged, and so it's just we're going to have 2 tests and an exam. I've taught this now maybe 2 times, and I think there's a fair number of questions out there on my web that you can practice with. Thoughts? Oh, this is just kind of saying kind of what I said already, is that I'm doing it different than George was doing it. And it kind of outlines the philosophy and the sort of general course technique. Quite frankly, I wrote that more for other professors who were than for you, but it's good to look at. This is my timetable. So it basically says I'm going to be here Monday and Wednesday. So you can find me in between my 2. I have to still be here by 4, so I'll be around. We have to think. So for office hours, I find the easiest to do is find this room and the other room. We're in a room that we're going to have to find. I've never been there. They're both booked after. But if we can find a place, maybe even in the hall, that we can talk immediately afterwards, then that's usually the best, because we're all here anyway. These are the dates. I just guessed how long we're going to spend on each topic, but it really depends on how many questions you ask, and I keep adding things to the slide anyway. So when people aren't understanding things, which is usually, then I make more slides. I'm a bit of a PowerPoint slide making addict. So there's so many slides. And then sometimes I worry that it just feels like it's too much, right? But they just keep going over and over the same material in different ways. And so maybe, in fact, you can kind of give me feedback if you want and say, hey, this section of slides didn't help. You can cut them out. So this is just the course calendar. Oh, the enrolling says if you're not enrolled in the course, then I have no power to get you in. But I always tell the office that everybody's welcome, and just keep coming and keep doing the things. And it's always the case that eventually you get in. And it's not like we're full here, right? People can, on that, my personal belief, this is a message to the people in the back, that the closer you are to the front, the more likely you'll talk to me and the better you'll do. So feel free even to come down here. Mental health, you know, we all have our moods up and down, and don't be alone with them. If you're upset with anything in the world, you know, you can write me. There's that link tells you places on campus that you can go. This is the E-class that doesn't do anything. Here, how do you, somehow you turn it on. I don't know, I'll figure out how to turn it on. But as you see, it doesn't say anything. Zoom. This course is fairly new to me, so hopefully it's recording correctly, and we'll get new versions of the videos. But every topic has videos already. I'll show you where they are. In fact, this is the last time I taught it. Oh, I guess you have to sign in to get them. But those are the videos from last term. I never did get around to putting them in here. So here's a list of every topic, and here's the video. This video, that one is 11 minutes long, and you can watch them. And so those are previous terms. And last time I taught it, I hired somebody to do the editing. It requires cutting them up into pieces that fit these topics and giving them good names and posting them. All right, so what else we got here? Solutions, there are no solutions there because we haven't had tests yet. So here are the topics we're going to cover. Here, but we probably won't get, we'll just get down to about here. Here are the slides. This here is illegally stolen. It's the 1019 book, which I taught once, and it's the chapter on logic, if it's useful. These are, I have a computer, an algorithms book, and I was trying to get a chapter of logic in there, but they didn't let me put the chapter of logic, so that's the logic chapter. Here's some practice tests. These tests, I guess, or assignments from before. This says, I talk too fast, try to get me to slow down. Good way to study is you go through the slides and you think about what's on the next slide, right? Because slides kind of pose a question and then answer it. So you can not flip forward quickly, but pause and think, why are we doing this? What does it mean? What's the answer on the next slide, right? Oh, by the way, we don't have, there it says no text required, right? It's everything, yeah. Yeah, so that's, that's what these are, right? Each one has questions. Oh, we didn't really get much past this. I guess we did induction and computing, but then these are just the old tests and stuff. So I didn't edit them to topic. All right, so this is just other people's notes. Here's my logic that you've seen already. this is just saying that what year the videos come from. We're not going to do the intro. We're just kind of chatting about it here informally. So our first topic, which we're going to start today, it just deals with variables that have values true or false. And you say and or and not and implies. And I mean, I always think everything is easy, right? But it's not that hard. But despite that, we have a lot of slides on it because there are different ways of thinking about it and different ways of proving things about it. And then we go on to predicate logic that has the variables then can take on objects from the universe, right? And then we can say for every person in this room, there exists somebody who, right, that they like to talk to. And this section focuses mostly on the game, where there's a prover and there's an adversary and there's an oracle that's helping out, and we talk just like the game that we did, right? Yeah, so that's all of that section, right? And again, look at there's lots and lots of slides, lots of examples, and then we go over to more what George was doing. What does George's formal proof system look like? And quite frankly, he and I just, so his proof system at the core is just, there's so few things you can do, so the proof has to be very complicated. And then he has theorems that if you do this, then you can prove that. And so you never actually even prove things. You have theorems which proving that a proof exists. And it's like, Lord, come on. And it depends on which kind of theorem you're in. So I changed the proof system a bit, bringing in new notation. But in the end, it boils down to the same. And when I first started with it, I didn't get it at all. It's not the way I do things. But I'm myself even, I'm just now starting to see how my games and these formal proof systems are sort of the same. If you do the proof one line at a time, then it's hard to know what it's doing. But if you do it kind of like recursively, then it kind of makes more sense. We probably won't spend too much time on syntax. The induction, inductions is important, and I got some good examples here connected to algorithms, and hopefully we'll time to do them. This is basically doing 2001. There's various logic courses. Let me give a little bit of an advertisement for this course. So you take any math problem and it can be translated into this logic, which is called first order logic. And then you understand these games, it can lead you how to prove it, and it can really help you in pretty much any course. So when I've been teaching this, people come to me with their calculus, because in calculus they do crazy proofs, and they don't tell you how to do for all exists proofs, right? They'll say for every epsilon there exists a delta, but do they even tell you what that means, right? More or less how to go about proving it, right? And if you get this sense of how to prove this, it's just going to help you with everything. Like all these topics, those lines there are the main things that you do in 2001, right? And the reason I wanted to teach this course is I was teaching 2001 many times, and people just didn't understand the logic, right? How can I teach you something complicated when you don't know what for all exists means, right? So I really do believe that if you understand this course, it'll help you in actually in life, right? I think some of this should be taught in kindergarten because, when you look at the internet, people clearly don't have very good logic, right? So that's all right. Any thoughts? Everybody good? All right. So we can dive right in then. And yeah, feel free to pause and chat. Yeah? This course? Oh, this, right, right. You mean 1019 versus this? What were the? Yeah, yeah. All right. So in those 1019 courses, there's a section on logic, and people don't. I was trying to cram more in when I was teaching it, but I don't think other people were spend that much on it. And maybe they do it different than me, and that'll give you. I think having more ways of doing it is the better. I'm certainly starting assuming that you know nothing. All right. So I'm at no point will I assume that you've taken anything. All right. And if you don't understand something, it's your job to holler anyway. So don't worry about that. Yeah, forget about prerequisites. We're going to start right from, I'm going to assume you know nothing. And if you seriously, if you're not understanding what I'm saying, holler, right? Don't worry about being embarrassed that you don't know something, all right? Because people find this hard. I was talking to him, he said he found 1019 hard. He finds this, he's going to find this hard, right? It's hard, right? We're at university and it's hard, right? So really don't be shy, all right? All right, this is just saying it's hard. That's the first line, right? And we're just looking at and or implies and proofs. And in fact, I made it this page of a bunch of rules. And quite frankly, if you really understand this page, then that's all this section of slides is covering, right? And what it sort of says is, look at the cases one. It doesn't get harder than cases, all right? What it says, if you've already proved, how can I prove, can everybody see the one? So gamma is this funny letter here. I'm trying to prove gamma, right? And I say, well, there's two cases. And you'll see the first thing, I prove to you either alpha is true or beta is true, right? That's just saying I've covered the cases. If I prove it in the case where alpha is true, right? See, that's what I do is I say, suppose alpha is true, then I prove gamma. Then suppose beta is true, I prove gamma. Now, I know that covers all the cases because either alpha is true or beta is true. And then I conclude that gamma is true, right? Everybody see that? That's proof by cases, right? On one side, I can say it's hard, and on one side, I could say, Well, you probably did it in high school. Yeah? I would say you should memorize it. And the reason you should memorize it is because it's just so core. You should know it. In fact, I take it back. You shouldn't memorize it. It should be in every cell of your body is the truths of the universe. Right? I will say that I think last term I made them write the whole thing down on the test, right? And all right, so that's the kind of thing we're doing, right? That's this section of slides is saying we're trying to prove things and we're going to use rules like this, right? And how do you structure your proof? Any questions about this? All right, I'm not going to go over them all now because that's what the whole slides are, right? It's going over these. All right, so let's just start with some example that came up on my internet. All right, here we have a statement. All snakes are reptiles. Some reptiles hatch their eggs themselves. All right, those are facts. And we want to know, can we conclude that some snakes hatch their eggs? Yes or no? All right, everybody think about it, right? Snakes are reptiles. Some reptiles lay eggs, right? So how many people think that proves that snakes lay eggs? How many people think it doesn't prove? See, you guys all passed already, right? This is as hard as it gets. All right, so how might we argue this, right? So again, conflicting with George. He says he never talks about universes, but if you don't talk about universes, then how do you know what we're even trying to prove, right? It's tempting when seeing this to say, I know that snakes lay eggs, so I'm going to just say yes, right? But we're not talking about Earth, and we're not talking about snakes. We're talking about snakes in every possible universe, in which are the things that we've stated are true, right? So if I want to, I'm not trying to argue that whether or not real snakes lay real eggs. It's about whether it follows from the things we've said, right? So don't get confused by reality, right? You know what I'm saying? So in order to prove that it doesn't follow, all I have to do is describe a universe in which the things that are the axioms that we start with are true, and the statement we're trying to prove is false, right? And there's different ways of describing a universe, but here's a picture, a Venn diagram that's kind of useful, right? The box can be the set of all animals, right? For every object, we put it in there if it's an animal. And the blue circle is the set of reptiles. And we got the circle which of the animals that are snakes and the animals that hatch eggs, right? And you'll see if this was our universe, that animals were laid out like this, then is it true that all snakes are reptiles? You just look at the picture. If you're inside the snake circle, you're inside the reptile circle, right? And then it says some reptiles hatch eggs. Well, the ones that are hatching eggs, right? So look at there are reptiles that hatch eggs, right? And the snakes don't. Right? That's all there is to it. Right? Everybody kind of follow that? And right, and that's where we're using our intuition as well. We're imagining other universes where things may be true and may not be true, right? All right, so this just says one counterexample is enough. right? You see, I gave this counterexample universe in which this doesn't follow, and hence you can't prove this from this, right? If what does a proof mean? If I can, from this, I can prove this, then it means in any universe in which these things are true, this thing must be true as well, right? And if I want to prove that it's not true, I just need one counterexample, and then it's not true in every universe, right? Does that make sense? Good. You guys are really good head checkers. And if you guys do that for the rest of the term, we will love each other. All right? So here's another one. Again, we got snakes or reptiles. All reptiles are animals and lay eggs, right? Many snakes have one lung, right? Okay, there's what we got. And now what do we want to prove? Prove that there are animals that lay eggs and have one lung, right? So think about that one. Do we know that there are animals that lay eggs and have one lung? Everybody, yeah? You have a question, or you're just saying yes? Yeah, everybody good with that? So, right, so here's well, now I give you a proof, a picture. I'm giving you a picture, but it's describing one universe, right? And maybe it's a general enough universe that it convinces you of something, right? But be careful of proof by example, right? Because we want to prove it's true in every possible universe. So describing one universe doesn't do the trick, right? But you can kind of see, though, that we still got that snakes are inside of reptiles, and we still got all animals lay eggs, right? Sorry, all reptiles, right? Everybody in the reptile are laying eggs, and some snakes, I get, right? You can, yeah. Oh, about the lungs?
Yeah, because we haven't proven that other reptiles have only one.
Yeah, that's a very good question. And the reason I did it is because, yeah, I don't know whether in other universes there are animals with one lung that aren't snakes, right? But I'm trying to give as general of a picture of universes as possible so that we can we want to prove it's true in all universes, right? So maybe we don't know whether there are one lung other animals, right? And is that going to make our statement not true, right? So I was trying to make it as general as possible to see that, yeah, in every possible universe, it's not true, right? And in this picture, that little piece of one long non-snakes could be empty, right? There could be nothing in there, right? Does that make sense?
Yeah.
All right, so how do you prove, right? This says a proof by universe doesn't work here because we need to prove it for all universes, right? In fact, I like these games of adversaries and stuff, right? So I would start by saying, adversary, give me your worst case universe, right? I know nothing about the universe other than what the axioms say, right? And what are we trying to prove? We're trying to prove some animal has this property, right? Well, that's basically an existence statement, right? There exists an animal. And how do you prove that something exists? You construct it. You say, there it is, right? You build it. So we're going to have to in fact, just off the top of my head here, there's one danger is that there are no animals at all, right? Suppose you go up to Mars. Is it true that all snakes on Mars are reptiles? It is true, even though there are no snakes. All of them that are there are reptiles, right? So you got to be careful about these weird cases, right? Now, the only one that might show that something exists at all is the fact that we say many snakes. That kind of implies that there are snakes, right? But if we want to do an existence proof, you gotta first worry about, does anything exist, right? So, all right. So, oh yeah, this just says, how do you do this in your life? Well, you have a question in English. You try to translate it over to the math of the logic. You prove it in the logic, and then you translate it back to English, right? So here, let's try to do it here. Our goal is to prove that there exists, and backwards E, if you don't know, backwards E is the exist statement. It says there is an object out there with the following property, right? So we're saying what we're trying to prove is that there exists an object X, right? And the object could be a banana. It's just there exists an object that has the following properties. It is an animal, it is an egg, does lay its eggs, and it does have one lung, right? Everybody kind of get that? Those are little statements about it. You know, animal X, you give it a banana, and it tells you yes or no, is it an animal, right? So these are returning yes and no, and then we put ands between the yes and no's. And then what do we know? How do we prove that? Well, the first statement is we know that for every object, if it's a snake, it's a reptile, right? So we want this to be true for every object. So is it true for bananas? Is it true for a banana that if it's a snake, then it's a reptile? It's still true. It's not a snake. But if it were a snake, it would be a reptile, right? Right, so that's still true. It's true for every object, right? And the other one says for every object, if it's a reptile, then it's an animal and it lays eggs, right? That's our second statement. And our third statement says that something exists, which is good, that there are objects in our universe, right? There exists something that is both a snake and has one lung, right? That's kind of, we're getting it from many snakes only have one lung. Well, we don't need to know that there are lots of them. We just need one, yeah? Good question. So he's asking, should we have some sense of what the universe is? And I'm going to say very clearly no, right? Because we want this to be true in any universe. If you go to a universe in some far galaxy and they have objects and they call anything yellow an animal, then that's their definition of animal, right? We want this to be true no matter what you define an animal to be, no matter what you define a lung to be. It needs to be true in every universe, right? Our objects could be integers, and you call some integers animals and some you call not animals, right? That could be fine. You see that? Right, so we're really trying to make our definition of a universe broad so that we can see it's true in every universe, right? Because the danger of you saying, oh, my universe are of animals, then you're arriving with the preconception of what does it mean to be an animal, right? And you might use some of those preconceptions to state things that are true in our system that we don't know are true, right? You might say, well, it's alive. Well, I don't know, it might not be alive. It might be, right? Does that make sense? Any other thoughts? Yeah?
There exists an animal, which is a snake, and has one lung. Would it be different than there exists a snake? If there isn't a snake, then it has one lung. Can we use implied?
Well, the one thing you said, if it's a snake, then it has one lung. And is that true? Do all snakes have one lung? No, it's not, right? You want to be careful that we're not saying they all have one lung, right? And you raised an interesting thing. If this says for all objects something is true, and that's, if we're doing formal logic, that's the way you have to do it. But you said for all snakes, right? And that's a standard thing that we do in informal world. We'll say all snakes, right? And you'll see, in fact, the top one says all snakes. And instead of say, I could write for all X, that's a snake. It's a reptile, right? And we're gonna informally look at doing it this way. And informally, that's a nice thing to do. And this is informal. Informally, you're allowed to do this. Formally, you're supposed to do that. You're supposed to, when you say for all X, it's over the entire universe of objects, right? Everybody kind of get that? But we're going to do this all the time, right? Because we're just used to it. And because just even in this example, this is neater than that, right? It's more kind of compact and obvious. All right, so all right, so now we're going to start the proof, right? And what we're trying to do is we're trying to construct something. And the only way we know something exists at all is from 3, right? 3 says something exists with a certain property, right? And if I was an oracle assuring you that an X exists that has this property, then one thing that I would do for you as an oracle is whenever you ask for one, I can hand it to you, right? That's the job of the oracle, is I'm claiming it exists. You say, oh, it exists, great. Give me one, right? And I'll give you one, right? So that's what our line 4 says is okay, something exists. What does it mean for something exists? That means I can hold it, right? So, and give it a name. So here we're introducing a name to it. It's capital X. And you'll see I got a little x in line 3. There exists a little x. And in line 4, I have a capital X, right? Are those two x's different? They are different. And the difference, it's kind of like suppose you had a little loop in your program that looped over I. The I is local to that little loop, right? It's not little x is not a specific object, right? And now we're talking about a specific object, and we want to give it a specific name. And so we're going to give it a different name than little x, because that gets confusing. Having our little, if out here, out of our loop, we had the variable I, that would be confused with the local loop I, right? So we're going to have this object who we're going to call capital X. And what do we know about it? We know that it's a snake and it has one lung, right? And we get that from X, from statement 3, right? Everybody follow that? And then, well, if you go back to our purple table, there are various rules. And one of the rules says that if something is a snake and it has one lung, then it's a snake, right? It seems obvious, and it's all going to seem obvious, but it's still, what we're doing here is we're kind of defining what and means, right? In our universe that we're off somewhere, they might even have a different definition of and. And we have a rule out there what and means. It's the purple table somewhat. It's defining what and means. It means if this and this is true, then they're both true, right? That's the definition of and, right? So it's a snake. And it's the, here. No, now what we say by 1 and 5. Well, 1 says if it's a snake, 5 says it's a snake, and 1 says if it's a snake, it's a reptile, right? Hence, it's a reptile, right? And let's see, 2 says that if it's a reptile, it's an animal and it lays eggs, right? That's what 2 says. And so we have, it has all these properties, right? And that, then if I have an object, if I say, hey, object X has this property, then what does exist mean? It means that there exists something. So then I can conclude that there exists an object that has this property, right? Going from 8 to 9, I've dropped the name capital X, and I went back into a local variable. I'm no longer saying who that object is, what his name is, right? I'm just going to the fact that such a thing exists, right? Everybody see that? Right? So really, this is pretty much as hard as it gets, right? So if you can kind of do this, you're going to be fine. And my goal of starting with this example was to kind of show you, this is kind of a summary of the whole course, right? This is what we're doing in this course. Yeah? Of what variables? Well, let me tell you, answer a different question. The TAs aren't always as brilliant as I would like them to be, right? And in fact, at the moment, I look at the TA list, we don't even have TAs assigned. So you can kind of guess when we do get them assigned, they might not be logic experts. So one of the things, so when I started teaching, which quite frankly was before you were born, I was a hippie and said, oh yes, do everything your way. There's so many ways to do things, right? And the longer I teach, the more I get down to, no, don't do it your way. Don't, please. Do it my way. And why do I say that? Well, because the people who understand the material, they tend to do it my way, because they learn the way. They say, let's do it. And the people who don't really get my way do it their way, which is usually wrong, right? So that's one thing. And the other thing is, here's a little hint about my test. I try to make the question so that the answer is as unique as possible. And one advantage of that is it makes it easier for the TA. And if you kind of go off script, then you're going to mess up the TA. Right? Now, I didn't get the nuances of what you said, and maybe what you're saying is fine. And we're definitely going to talk about how how I write these things out. And if you use Y instead of X, it would be fine. All right? Yeah? Like what we did here? Yeah. So in the past, I haven't done a lot of, one of the hard parts about doing this logic is translating it from the English to the math. And maybe we should do more of that in this course. In the past, I haven't spent much time on it. So in the past, I would give it to you. I would give you line 2, 3, and 4, the ones that are axioms, and I would say, and then you need to prove this, right? So, but yeah. Oh, over here. Absolutely, you need to do this. Oh, what the rule's called. Yeah, this is just a warm-up, and ideally you'll say, for this section of slides, for example, there's the purple table, right? The one that we saw already. And you should have the purple table just in your gut. And then if you're saying by cases, then you write by cases, right? And quite frankly, it really helps the marker too, because the marker is trying to figure out what are you doing and why are you doing it. And you just write another line down, and it's like, where did this line come from? What are they doing? I don't know. You don't want to make the poor guy work too hard, right? And if you say this is cases, then she can look up and say, was this from these line 1 and 3 and 8 cases? Did she do that correctly? Bang, we can say, yeah, they did it correctly, right? It helps the marking tremendously, and it shows that you know what you're doing. So I'm going to go, yes, do that. And why didn't I do it? It's because we haven't defined them yet. And it gets squished on the slide. Yeah, I mean, this is all a little bit more informal, right? So then we translate it back to English, right? Everybody good? All right. I think these. That. All right. So this is just saying you go to a restaurant and you want to use your logic, right? So here we have an and an or. What do and or mean, right? And I'm sure you would all translate this into, let's go click back on it. So we're here. Is you can have ham and eggs, right? Or you can have porridge, right? Everybody get that? Now, what's the difference between their or and my or? What if you said, right? So here's the thing: is true or false? Does that evaluate to true or false? True. True or true? Is that true or false? In our world, it's true. Is it true here? No, she's not going to give you both, right? So her or is what we call an exclusive or, right? You write it down like this, right? So that's one difference. All right, so now let's do it again. You can have coffee and eggs or porridge, right? Now, what do you think this means? You can have coffee and you can have eggs or porridge, right? Everybody agree that that's what it means, right? And the interesting thing is that menus usually are very bad with brackets, right? You see that the brackets are different. We interpreted these things in different ways, right? Are people kind of buy that? And so that's just the thing to be aware of. And when we go from, why do you, George will say, you don't do informal, you don't do intuition, you do formal. And this is I'm putting words in his mouth, but I would say that this is an argument for being more formal, right? You got to know where your brackets are. And I'm pretty sure that the way, if I say 3 times 4 plus 7, you put the brackets around the times. Here you would put the brackets around the and first, the top one. But I would say, let's try not even to use that. Let's always put the brackets in so we know what we're doing. Yeah? Uh-huh. Yes, she's not going to give you eggs and porridge. I would say if you go into a restaurant, the assumption is that ors are exclusive ors, right? All right. You know those buttons that you can move to the next slide? Do you know why I don't have one? Because I talk too fast. And if I walk over here and I have to walk back, it gives you time to think about things. Right? Exclusive or, inclusive or. All right. Let's do another example. I don't know. Do you guys, Clue was a big game when I was a kid. Maybe you don't know it. But we can have, this is a true-false variable. It says, Mrs. Peacock loves Colonel Mustard, right? That's either true or it's false. And in some universes, it's true. And in some universes, it's false, right? In some universes, Mrs. Peacock is a banana, right? And love means whatever you want to mean it to mean, right? All right. Colonel Mustard loves Scarlet. It happened in the kitchen, right? Miss Peacock committed the murder, right? These are all statements, right? And we want to form various logics. We can say, well, if the first 3 are true, then we can conclude that the last one is true, right? And we can write that down as a statement, right? This again, here, I didn't put in brackets, right? I kind of lied to you. I said always put in brackets, and here I didn't put in brackets, right? So you do need to know that the ands are tighter than the implies, right? So if these 3 things are true, then P is true, right? And, I have a brain that can remember some things well and can't remember others. And I have been doing logic for the longest time, and I always still struggle with that this one is and this one is or, right? So that's, sometimes I write the little and above it. That was a cheat for you guys who don't know yet, right? And it's not in all of my slides. So you're gonna have to learn that this thing looks like an A, and so it's for and, right? All right, so if all the left are true, then the right is true, right? And then we can do what's the contrapositive. I even don't have the purple table memorized. Which rule is this? Is this contrapositive? Or anyway, we can flip it around. Suppose I know that Miss Peacock didn't do it, right? If I know that P didn't do it, what can I conclude about the other things? What can I conclude? Oh, he's brilliant. Not only did he know to negate it, but he knew to switch the ands to ors. All right? So he applied 2 rules there, right? right? If P is not true, then the and can't be true, because if the and was true, then P would be true, but P is not true, right? So we know that the and's not true. And then you have to do another step. You say, well, if the and's not true, why is the and not true? Well, they can't all be true. At least one of them is false. So we get the or of the negations, right? We bring the negation in, and that's called, what is it called when you bring the negation in? De Morgan. De Morgan. All right. Yeah, and to answer your question, I think, if your brain freezes and doesn't remember that that one's called De Morgan's, and you wrote down, oh, that one where you bring the and in, I'm good with that. I would give you gold stars for, doing what you can do, right? You can see I don't remember De Morgan's name. Oh, on that topic, count on it, I will never remember your name. So if you're writing me emails and you want me to know who you are, send me a picture. If you want to be anonymous, just send an email and I will never know who you are.